Good morning, student. This is our last chapter, chapter 12, regression and coloration. This is the formula that we will use often in this chapter. It's called the coloration. This is a phone factory. They found out the formula to make the phone battery last longer. It is to add the germanium, a kind of the rare earth. Add more germanium, it might impact the battery lifespan to last more longer. Now we want to check, is there really the relationship between the adding more gram of germanium causing our battery lifespan last more hours? Yes, we later can use this formula, the correlation formula, to find is there a so-called positive and is it a strong correlation or not. Okay, this is 6 possible numbers that correlation can produce. The number will be between -1 to 0 to +1 based on the correlation formula here. What is the meaning if we get the number is -1? After we do the long calculation, -1. This means that we have a very negative correlation. This means that add more germanium cause the battery perform bad. The hours will drop. A perfect negative correlation. What happened? Let's say we get a number close to -1, negative 0.94. This is a strong negative correlation. This is also a bad thing. Means that more germanium insert into our phone, it causes the battery like perform bad. What happens if we get our R after the calculation? It's a positive 0.6, quite close to +1. This is a very strong positive correlation. Means that more germanium we add into our phone, our battery will last longer. A good thing, a good sign. We look at the previous case that we studied about the phone, and we want to compare with the new problem later on. Okay, this problem we had discussed 1 week ago. There is a factory, and the factory is producing one model of the phone. It's called the phone G1. And at this moment, we are using the old machine to produce the phone model G1. And the old machine producing the battery lifespan is average 200 hours every time we fully charge it. But a few days ago, this factory, we just imported a new machine. And we are not sure that the new machine will cause the battery lifespan to change or maintain the same. In this case, we want to check whether our new machine still having the same battery lifespan production or not. So we're going to write that yes, the old machine and the new machine going to produce the same 200 hours average of our phone battery lifespan. Or another possible conclusion is no, new machine have some setting causing the difference battery lifespan. In this case, we're going to use the one independent sample t-test to check the claim, which claim is valid. So we're going to follow the 6 steps, starting by writing the possible conclusions. And then based on the problem, we identify that we're going to use the one independent sample t-test. And then we want to know what is the scissor line to cut between the which conclusion we're going to so-called reject or do not reject. And the fourth one is what happens if after the calculation, the number is inside the tail or is inside the big area. Then step number 5 is after the calculation, this is our number. And now we can determine that this yellow color number negative 0.467 is inside the tail or is inside the big area. For this case, it is within the big area. It means that we do not reject the old claim, or to say that we maintain the old claim stating that, oh, new machine, old machine, same, 200 hours of the phone. Now we look at our correlation situation. What is the difference between the scenario? Just now is so-called one population, just the phone G1, and then we have a one properties, one factor, that is the phone hours. Now this is the problem while reflecting the correlation. We have the same factory, and now this factory maintain the old machine to produce the phone. The only thing changed is the germanium, the component, they add more germanium. Okay, they are adding more germanium into the phone G1, adding more grams of the germanium. And they want to know that if the germanium will make the phone battery last longer. Before we proceed, we need to have some data. So the scientists, they tested 5 phones. The first phone, they added extra 5 gram. Germanium 5 gram, they found that extra 8 hours to the phone battery, plus another 8 hours. So they conducted the 6 gram, extra 6 gram, extended 9 hours. And until the 5th phone, it extended another 9 hours. For this case, we want to check, is there a relationship between the adding more germanium causing the phone lifespan will be longer. We're going to write the possible conclusion. The first one is, okay, adding more germanium, the lifespan of the battery, same. We add 8 grams, lasts for, at the end, the average to 200 hours. It will not have extra, let's say, plus 9 hours, no. Or else we might have the conclusion showing the germanium is powerful. It causes the battery lifespan to be longer a little bit. We're going to write that, yes, there is a correlation between the germanium gram and the phone lifespan hours. We have the correlation, which we use the row to represent the population, the big sample size correlation to be positive. Means that there is a connection between the gram and also the hours. Now we want to select appropriate formula to test for our significant or not significant situation. There will be 2 formulas within the step number 2 here. The first one, we still need to find what is the connection numbers between the grams and also the hours. Means that we need to use this formula, the correlation formula, to find the number. The number at the end will be between -1 to 0 to +1. What will be the n? The n is the total sample size that we did the experiment. We have 5 phones. So n later on will be 5. How about the x? X will be the independent variable, something we are controlling. We are controlling the grams, how many grams of the germanium insert into the phone. So x later on will be the germanium weight. The y will be the x will be the independent variable. The y will be the dependent variable. Means that we're going to see the outcome based on our grams. How to find so-called the summation of the x, summation of the x times y, the summation of the x square, y square. We need to create this table. so that easy for us to find the summation for each of the expression terms x, y, x times y, x squared, y squared. So we need to create that table. So easy for us to sum up all the terms there later on. So once we have the table, we're going to insert what is the summation for each of the terms there. Then it takes some time for us to get the number. So the number will be between -1 until +1. Okay, take some time to get this R. Then what happened to the R? There will be two things. The first thing is we know is this a negative correlation, or there's no connection, 0, or there is a strong connection, plus maybe 0.8. This is the first thing that are going to give meaning to us. The second is we're going to include the R into the t-test for the correlation formula here. So we're going to insert the R into this formula here to find whether that it is significant or not significant for us to proceed later on. So we're going to drop the R into the formula. The N will be how many sample size that we use for this experiment. So N will be 5. R will depends on the formula here, the number. Okay, next one will be step number 3, level of the significance. We want to know the line to differentiate between the tail and the big area. So for this case, we need to identify the degree of freedom. We need to use this formula, n minus 2. N is just 5. 5 minus 2, we have 3. And then we need to match it with our level of significance. For this case is 5%, 0.05, and this is a one tail. Why one tail, not two tails? It back to the definition of our alternate hypothesis. We are looking something that's greater than 0. Greater is far to the right. Only one tail. So we're going to choose the one tail. It's a bit small to see from the table here. Later on, you zoom it from the PDF given. We're going to find the intercept between 0.05 and also degree of freedom is 3. So the number is plus 2.353. This is the scissor, the cutting line between the tail and the big area. Step number 4 is what happens if the number, the t, is inside the tail. You're going to reject the first null hypothesis. What happens if the number when we drop is within the big area? Then we do not reject the null hypothesis. Means that we're going to accept the first conclusion. No connection, no relationship. Now we go to the step number 5 is putting the R, the N, the R square into the expression at the right here, and we're going to get the exact value of our T. Our T is 3.4641. When we take this number and we drop into the diagram, the bell-shaped diagram, we realize that it is very far to the right. It's very far to the right there. Here, this is the scissor line. Scissor line is 2.5. Our formula, what we get is 3.46 is inside the tail there. Step number 6, we're going to write a conclusion. We're going to say that, okay, since our number 3.46 is after the 2.35, the more than the level of the significance. So there is sufficient evidence to conclude that adding more germanium will cause our battery lifespan hour to increase. When we have a significant situation, now we can proceed with the next step. We can do a prediction using the regression formula. Okay, regression formula is similar to our linear equation formula, y equals to mx plus the c. For the regression, it's a bit complicated. This is the formula. The basis same as mx plus c. For this case, c is a, m is b, and x is the x. We need to go back to our initial table there. X is the germanium weight, gram. Y is the battery hours. So we're going to use the table, same table again, that contains the summation of the x, summation of the y, summation xy, summation x squared, summation xy, to fit into the given formula here. No worry about the formula for your exam context because you'll be given this formula. Now we're going to convert it to the numbers. So for this case, we're going to get a equals to 6.2 and b equals to 0.4x. This is the connection between the battery hours and also the germanium weight. Now we're going to do a prediction. What happens if the scientist, he is adding 20 grams of the germanium? What will be the extent hours of our phone battery? So when we added 20 grams here, we're going to extend for extra this hour. Regression, can we use it if it's not significant as steps number 6 there? No, we cannot use the regression formula. Why? Not significant means that we cannot do the prediction for a large population. So we cannot use the prediction to see it happens for the other cases. So step number 7, it depends on whether significant or not. We hope that it's significant because if yes, we have the formula to create a better phone. We know that the factor causing our phone can last longer, the battery more powerful, depends on the germanium. We have extra things that we can talk about the R here later on. Okay, just now, after we spend some time to get our R equals to positive 0.89. This is close to +1, means that it is a strong positive correlation between the weight and also the hours. When we square the R, what is going to happen and what can we say about? Okay, once we square it, we coincidentally get 0.8, the value. The 0.8 will say that the 80% factor causing our battery lifespan is because of the germanium. How about the another 20%? Okay, for this case, the 20% is not by the germanium. Maybe it's because of the temperature of the phone itself become one of the factor. What we can say when we square it is the percentage of the battery lifespan is because of our germanium factor. Okay, when we draw it in the diagram, this is what we're going to see. So just now, after we use the t-test, our number is the yellow color. It is within the small area here. This is a good thing for the factory. They'll know that, okay, germanium is the answer. Okay, this table is very helpful because it's going to help us easily to find the value of our correlation later on, the R, and also to find what is our regression, y equals to a plus the bx there. We will have a long formula. Okay, for the second case, this is the farmer situation. This one I will skip it because it's similar to the phone one case. We're going to follow the 6-bit step by defining what is our possible conclusions, and then what is the formula that we want to use, and then because we want to make a conclusion, means that we need to have the borderline to show that what is the number when we say that null hypothesis we do not reject, or we reject the null hypothesis. Okay, step number 4 is what happens if our number if within the tail or within the area. Step number 5 is now I'm doing the calculation. This is the number. Step number 6 is we're going to write the conclusion, saying that whether we do not reject or we reject, significant or not significant. And step 7, if it's significant, then we can proceed to create the regression connection between the, for this case, the tall of our tomato plant and also the fertilizer engram that we use. Okay, let us look what happened when our R from this formula is very positive, close to 1. This means that a very strong positive correlation, or to say that this brand fertilizer really helped the growth of our tomato plant. When we square the R, we get another number, 0.97. This means that 97% of our tomato plant height is totally because of the fertilizer. How about the extra 2% there, 2 to 3%? Then we have possible other factors, maybe the soil, or maybe the we have the worms inside the soil that how to say, contribute to the growth of our tomato plant. Okay, this is the diagram that we can draw for our fertilizer and tomato plant case. Okay, for the last one, you're going to do this problem on a paper. You are given the connection between the wick and also the height of the soybean plant. Somebody observed on the 7th day, there's week 1, end of the week 1, they found that it just grown the soybean, it is 5 cm tall. And then he do observation week 2, week 3 until the last week 7, that's the 49th day. And found that his soybean plant is 40 cm. Now for this problem, you no need to find what is the R. Instead, you want to find what is the regression line. We assume that it is significant, so we proceed to the step number 7 to find what is the formula to represent the regression between the height, the Y, and also the H, the X. So at the end, can you, on the paper, get the same number as this one? So this is your task. After you complete on the paper, submit it from, you can check the Google Form link inside the eCampus. Okay, that's all for this week. Okay, bye-bye.